Josh, thank you. The booklet that I gave you a few weeks ago now, the little booklet, the little pamphlet you guys crack open, 99.9% of that is still applicable to what you're doing right now. The only difference is what regression you run. You're running a quadratic one versus a linear one. That's the only difference. And hopefully the shape of the data shows you why you're going to run the other one. I'm going to go ahead and crack this open. So, here, I'm going to switch it over to here. Oh, you can't see this right now. Hang on. There we go. That's what mine looks like, huh? Which looks, if you remember, similar to the Excel graph we generated in class. The Excel looks prettier. It's got color. You can put text directly on the graph, which is very, very nice. Unfortunately, we don't carry Excel in our pockets, so we go with this instead. Please.
Oh, this is my TI randomly full line.
Oh, you already have the regression. It's okay, Josh. You're 30 seconds ahead of us. So what we're going to do is we're going to get the curve now, the best fit curve on that. So remember, you already have the scatter plot. You're good to go. You're going to go back to your stat menu. You're going to go over to your calculate menu. All I'm doing is I'm going through like page 3 of your booklet now, kind of rapidly. And then here is what you were using over the past couple weeks, 2-3 days. We're going to jump down to quad reg. When we talk about Usain Bolt, we'll use cubic reg. When we talk about the coins we're going to flip later on, we're going to scooch down to get something called exponential reg. All kinds of neat regressions. Fun stuff, fun stuff. And we'll see why you need each of them. Sometimes some don't fit. Sometimes some do. So I'm going to go down to quad reg, select it. I'm going to stick it in Y1. This is the same thing, page 4, first paragraph of your booklet. And then, when it does that, you get the coefficients on your quadratic. Let's make this a little bit darker so you can see them. I wrote it up here as well. But now tell me what it means. I see 2 variables, x and y. What are those variables and what do they mean? Here, let's x, y. What are these things? What are these things? Christina, give me one of them.
X is time
in
seconds.
You're the man. You're the woman. Not man, you're the woman.
I can do that.
Time in seconds. Time in seconds, because you guys were timing me in seconds, right? That is the independent variable. It's what you guys put in L1. That's what's on the horizontal axis. I wish the TIs would let you put text on the screen because it'd be so much nicer, but I wish all I wanted not going to do it. How about y? Absolutely. It's distance. In what unit? Yes. This is distance in feet. Now, it's been a week now. Not if feet, in feet. It's been a week, but if you remember when I had you standing down that hill over there, we ran the tape measure down, and I said I need 8 groups of 25-foot increments. Boom. There was your unit. So, what does the equation tell you? How is this useful to us? Oh, Brittany, please.
Because distance in feet divided by time in seconds is your acceleration.
Oh, it's our velocity. Good. Hold that thought. Can you give me 6.5, 7 minutes on what you just said? Yes. I want to come back to that, sister. I want to come back to that. Okay. So, more generally, why do we care about this equation? We're getting to why the cop points the hairdryer. That's the whole point of this, is talking about that hairdryer that gives you speeding tickets sometimes. Actually, the hairdryer doesn't. The cop holding the hairdryer does. But we're getting to what's going on with that hairdryer. What does the equation tell you? Let me ask a more specific but related question. Suppose I go to my table. This is a tool you guys taught me about. And I plug in x equals 7. And I press enter. And y comes out 103, just about 103. What does that ordered pair mean? 7, 103. What does that mean? So me?
It means in 7 seconds you went almost 103 feet.
Very nice. So, at 7 seconds, I was at 103 feet down the hill, according to my best fit line. Now that might not have been exactly accurate, right? It's still a best fit line. But on average, based on my data's performance, after 7 seconds, I'd be 103 feet down the road. Is that okay? And that's just recognizing the units. Your project next week is all about units and dimensional analysis. I want to kind of preload that idea today, because it's crucial today, especially with what Brittany just said about acceleration. Very nice. I want to come back. It's about 4 minutes out from your comment now, Brittany. We're getting there. So if I put in 2 for x, if I put in 2 for x, I get 7.78 seconds. Okay. Which using Sumi's template, actually, Chrissy, go, you had your hand up too. What does that mean? 2 comma 7.78.
In 2 seconds, you will have gone approximately 7 feet.
We'll call it, yeah, 7.78 feet. We'll call that 8 feet, right? Yeah. Good. I like that. So I'm going to put in 4. So I'm going to predict, if it takes me 2 seconds to go 8 feet, I should go 16 feet in 4 seconds, right?
It should be double the.
Aha, I should if I were traveling consistently linearly. But I'm not. That's the problem, right? That's the problem. I'm not traveling consistently linearly. What am I doing, Brittany?
You're building your acceleration.
I'm accelerating. Good. I actually jumped the gun quite a bit on that one. Good. What you brought up. The idea of quadratic behavior of data is the data's y values are accelerating over time. When you're moving linearly, there is no acceleration. Constant velocity. For every second, you go 20 feet. That's what happens when you average out over time. You average it down to a linear consistent. If you know you can average 50 miles an hour from here, I think I asked you this question during the class. How long does it take to get to Boise? You guys said 6 hours. I said, well, how do you know it takes 6 hours? Like, well, when I average 60 miles an hour, and it's 360 miles away, 360 divided by 60 is 6. For those of you that can do that math in your head, the next project is going to be a breeze. If you can't, that's okay too. I'm not saying the project won't be a breeze. I just know if you can already think that way with the unit analysis, you're preloaded for that one. But that's the idea, that even though you average that over the whole trip, that isn't what is actually happening at a specific point of the trip. It doesn't take into consideration the stuff that you stopped in Burns to take a picture of a water wheel at 7 a.m. where the water was dripping off because it was gorgeous. And I stopped there for half an hour because I couldn't believe how pretty that was. I stopped to take a picture. But that's part of my time for the trip to Burns, right? And if I want to average 60 miles an hour, that means I got to make it up somewhere else. But don't worry, because Idaho, it's now 80 miles an hour from the state line to wherever it is. But that's the idea. We're not moving linearly on this bike. Now, if you remember, and it's okay if you don't, I actually drew up a little chart yesterday that showed this. Right? At 2 seconds, I'm at 7.8 feet. At 7 seconds, I'm at 103 feet. At 8 seconds, I'm at 135. And what you noticed was the jumps from second to second vary quite a bit. They get longer distances with each passing second. This is because, Brittany, we're accelerating. You see? So this over here is the column of the acceleration. Now, you don't have to memorize this. But the acceleration is in the rate of change of the rate of change. That's why I fixed your language a little teeny bit, Brittany. When you said feet per, you said feet. I forget how you said it. You said it beautifully though. You were missing one word second, I believe. If you said it, I missed it, and I apologize.
I said the distance. Y is the distance in feet, which is divided by the time in seconds to get your acceleration.
Put the word squared after seconds, and I'm a happy guy. Okay. So now that's going to sound weird to you guys. Think about why. You take the first difference, which is feet per second. This is feet, this is seconds. This divided by 1 second is feet per second. Hopefully that makes sense. Feet per second, feet per second, feet per second. This over here is analyzing feet per second per an additional reference to seconds. So it's feet per second, which is feet per second squared, which doesn't make a whole lot of sense. I agree. Right now it's like, I don't get that at all. That doesn't make it. That's okay. Here's why it has to be that way. It has to be that way because right here, when you take x and square it, you have taken a second and you have squared it to create second squared. You have to get rid of that to knock it back down into just feet. So if you're multiplying by second squared here, you have to divide by second squared here to cancel off the second squares. So mathematically, unit-wise, it actually makes sense to have feet per second squared. Because feet per second squared times second squared, I saw Jury, you went like this, I love that. Because she took feet per second squared times second squared, cancels off, and you're left with just feet. Now, if that seems like living in sin to you guys, that's totally fine. The whole project next week is all about that kind of stuff. It's about dealing with these kinds of units that come up in your daily lives. Sometimes you don't realize it, but you have to realize it, because sometimes these things are taken advantage of or just straight up mislabeled. And but you can catch it when you're buying products, when you're shopping for things, when you're comparing news media sources. You've got to make sure apples to apples. Apples and oranges are cute. You can put them in a bowl together. But statistically and mathematically, you cannot combine them. You can't add a gallon to a foot. You can put 1 + 1 and make it 2. But you can't add a gallon to a foot. They're totally different units. And that's why you have to make sure the units agree. We'll assume they do today. Because they do. Because the math works out. Because you guys collected great data. We're going to run with it. Cool so far? Okay, so we are now here. We now have a beautiful graph. Where's my best fit line? Oh, here it comes. Or curve, I should say. It fits beautifully. Fits beautifully. Now, let's answer some questions. Because now I want to bring in the new idea. I want to bring in the hairdryer idea. Put this here. I want to draw on this today. Can I zoom on this? I think I can. Zoom. Here we go.
For some reason, it's not making, now mine's not making the best fit line.
Did you put the Y1 after the quad reg?
I did.
And hit enter? And press graph.
Yes, it is, because that one's on. I was looking at this.
So, here is our data. What I'd like to know first question towards figuring out how, because the question I left you with last time was, how fast was I going right there? Right? How fast was I going?
Is that 200 feet?
That is 200 feet. That is the last point that you guys were measuring. My 200-foot group was at the bottom, bravely down the hill. I had to walk back up when we were done. What time did that happen according to your model? According to your model now. Let's do ourselves a favor.
Yeah.
Let's do ourselves a favor and turn the scatter plot off for now. Let's turn, here's an easy way to do it. You ready? Here's an easy way. Press the Y = button. Put your blinker up on top of plot 1 and press enter.
How did I check that?
And then just press graph
How
again.
did you get to that?
Press the Y = button.
Oh, just press Y.
Yep, press the Y = button.
Oh, okay.
It's okay. This is just a shortcut. You can do it a different way too, through the
Plot
booklet.
one.
But this is and then just put your blinker on top of plot 1.
Uh-huh.
So we still have our line though?
Yes, ma'am, ma'am. Yes, yes, yes. So you press enter on plot 1, it will become unhighlighted.
Oh, there you go.
And then press graph again, and you'll still get the curve. There's your curve. Yeah, I don't want to lose that.
Oh,
I don't want to lose the curve. I want the curve. The curve is the best fitting polynomial. But the scatter plot, the problem is the scatter plot's going to get in the way, because the scatter plot is the data we collected, but it's not directly on the best fit curve. Does that make sense? Okay. So the question I have for you guys right now is, at 200 feet, what time was that at 200 feet? 9.726. That's from data, right?
Yeah.
Find it on the actual equation. It'll be slightly different. Not much, but this is also exercising a math skill I want you guys to have. What x value is on this curve? The data we had from class was averaged out to 9.726. Yes, I'm looking at it right now. But what I want you guys to do is I want you to use your mathematics of your calculator or equational to let this equal 200 and solve this for x. Now we did this in class a couple days ago, and what you guys told me to do, you see how I drew this little dotted line right here? You guys told me to do that in a TI. Remember this? We can do that. Go back to y equals, go to y2, and put in 200. And what you'll see is, there it is, boom, much prettier than the one I drew because it's in a straight line. What does that 200 do to the curve? And this is the skill you guys reminded me of last time, was we could run the intersect command to figure out when y = 200, what is x over here? Let's do that. Second trace, intersect. Now it asks for some curves. It says, Should I use the quadratic as my first one? Yes. Press enter. Should I use the 200 as my second? Yes. Press enter. Guess, I never give it a guess. I'll let it figure it out for itself. 9.69 seconds. Notice it's a smidge different. It's a smidge different than what our data actually was collected. Yes, it's a smidge. It's off by about a tenth or a couple hundred, a few hundredths of a... But that's okay. It should be off. It's a best fit curve. It's not a perfect fit curve. I'd be nervous. I think we talked about this. I'd be nervous if we had the exact same times every single time. I think you guys are messing with me. So according to our curve, according to our data analysis, it took us about 9.69, took me 9.69 seconds on average to make that trip. Is that fair? Is that fair? 9.69 seconds to make that trip. What was my average speed for the whole trip? First question. Average